Back to the second set of problems. Today we are starting with the second set. These are simple examples, so let's look at them. Consider a room that is initially at the outdoor temperature of 20 degrees Celsius. The room contains a 40-watt light bulb, a 110-watt TV set, and a 300-watt refrigerator. And we also have 1200-watt iron. Assuming no heat transfer through the walls, determine the rate of increase of the energy content of the room when all these electric devices are on. So we have a room with all these appliances and their voltages are what? Given. So we should determine the heat energy that will be dissipated in the room if they are all turned on. This is very simple. So let's start with our parameters. We have a bulb, and the bulb is rated 40 watts. There is TV set. So the TV set too is rated 110 watts. A 300-watt refrigerator. So our refrigerator is 1000 or 300 watts. We have 1200 iron. They are all rated in watts. So assuming no heat transfer through the walls, we know for a room definitely there will be heat transfer through the walls. But assumption, let's assume there's no heat transfer and all these devices are on. How many heat rates will be inside the room? So first, if these are the ratings of what the electrical energy, let's add up all the electrical energy inside the room and check what we'll get. So total electrical energy. The total electrical energy will be the summation of energy by the bulb, energy by the TV, energy by the fridge, and energy by the iron. So the total electrical energy in the room is giving us what? 1600 and what? 50 watts. 1650 watts for the electrical energy. And we know from the conservation of energy that energy is not created nor what? Destroyed. But it's only what change from one form to the other. So if these appliances are consuming this amount of electrical energy, then we will assume that all the electrical energy is converted to what? Heat energy. So let's write that the heat energy or the energy content. The question even asks the energy content, and we know that the energy content can be electrical energy or heat what? Energy. So the heat energy will be equal to the electrical energy. Very good. So now we can work in what? Kilowatts. So our heat energy inside the room will be 1.65 watts kilowatts. Are we good? Or we can say heat energy in the room will be 1.65 kilojoule. Are we okay? So this is the amount of heat energy inside the room. You add up all the energy content of the various appliances. Can we move forward? Example 2. The lighting needs of a classroom are met by 30 fluorescent lamps, each consuming 80 watts of electricity. The lights in the classroom are kept on for 12 hours a day and 250 days a year. For a unit electricity cost, it is 11 cents per kilowatt hour. Now we should determine the annual energy of the lighting for the classroom. After that, we discuss the effect of lighting on the heating and air conditioning requirements of the room. So first, let's make the calculations. We write down our parameters and we can start with our work. So how many fluorescent lamps? Number of fluorescent lamps. So number of lamps. We got 30 lamps. Each consuming how many electricity? 80 watts of what? Electricity. So the consumption of the lamp, the consumption is 80 watts. Are we good? So the light is kept on for 12 hours a day. So for the 24 hours within a day, we switch on this light for what? 12 hours. So hours per day, that will be 12. And this light is on 250 days within the year. Out of the 365 days, this bulb operates for what? 250 days per year. So days per year, which is 200 and what? 50. And for a unit electricity cost, it is 11 cents per kilowatt watt hour. So we are going to, each consumption per hour is 11 cents. So the amount will be 11 cents. So how many cents makes a dollar? That will be 100. So when we get there, we will convert it and use it for our calculation. So now, if I have 30 lamps, each consuming 80 watts of electricity, then let's find the total what consumption for the lamps. So total consumption, that will be 80 by the 30, and that is giving me what? 2400 watts. Are we good? So we now have the total watts of the bulb. What about the hours? It operates 12 hours per day. So how many hours per year? So hours per year. You understand why we need to calculate for all these hours per year and the total consumption. So 12 hours per day and per year will be the 12 multiplying the 250 days. And we'll get a value for the total what? Consumption. Are we okay? So if we get the hours per year, then we know that energy. What is the formula for power? We know power and we know what? Energy. Let's get the value for the total hours per year. That will be 300 or 3000 what? Hours. So out of the year, this bulb is going to operate for 3000 hours. Are we good? 3000 hours. We have total consumption, we have the hours, and we know energy is what? Power times time. So if we want the total energy, we are going to find our power, which is 2400 by our time, which is 3000. This is for the year, because looking at the question, it says we should calculate the annual energy cost, the annual for the year. So the energy for the year will be the total power by the bulb multiplying the annual what? Time, which is 3000. And for the year, the energy consumption will be 7200 kilowatts per hour. The time is in hour, and we are getting 7200 kilowatts per hour. Are we good? For the year. And from the question, we are to pay 11 cents per every kilowatt per hour that we use. So if total we are using 7,200, meaning the energy cost is going to be, and I said 11 cents. If you are converting it to dollars, it will be 100, meaning this will be 0.11. Are we good? This is in something like pesos, and we are to deal in cedis. So let's work in dollars by converting the cent to dollars, which is, so we will multiply the 0.11 cent by the total energy, which is 7,200 kilowatts per hour. And in dollars, each year we are spending a dollar of 792.00 on the lighting of the classroom. Are we good? So it's very simple. You get your total power consumption, your total hour. This is an electrical question, but by the help of thermodynamics, we can also break it down. Get your total power consumption, your total hour per year, and you know energy is what? The power times the time. When you get your total energy consumption, you multiply by the amount to be paid, and you are good to go. This is for the example 2. Example 3, a very simple question. A person gets into an elevator at the lobby level of a hotel with mass 30 kilograms suitcase and gets out of the 10th floor 35 meters above. Determine the amount of energy consumed by the motor of the elevator that is now stored in the suitcase. So someone is in the elevator, and with a suitcase, the mass is 30 kilogram, and the person wants to move to the 10th floor, which is 35 meters above. We know energy is going to be involved, so we should now determine the energy that will be stored within the suitcase. Are we good? Because the energy consumed by the engine of the elevator will be transferred to what? The person and the suitcase. But we are interested in what? The suitcase. What type of energy will be stored? Remember, in the elevator, you consider the entire elevator to be moving, but inside it, the suitcase is what? Stationary. And what energy is possessed by virtue of position, which is what? Potential energy. Are we good? So we can get down. We have the mass to be. We've already solved questions on this. These are very simple questions, so you just have to brush through and go. The mass is 30 kilogram. The 10th floor is 35 meters above. So which is the height? 35 meters. So what is potential energy? But before you solve this question, you have to understand all the episodes we've already talked about, because it is very confusing to know the type of energy that will be stored in the suitcase. That will be potential energy. Because if you are considering kinetic energy, there's no velocity over here. Are we good? So the only energy by which we can consider will be the potential energy. And we know that our potential energy, PE, is given as the mass times gravity times height. We have our mass, we have our height, we know gravity is constant, so we can assume a value of what? 9.81. Always use your gravity as 9.81 for your analysis. So 9.81 meter per second square. Are we good? So we can bring it inside. So mass of 30, gravity of 9.81, and a height of 35. And our potential energy that will be stored inside the suitcase will now be 10 kilojoules or 10.3 kilojoules. Are we good? 10.3 kilojoules of energy. So if the person is to move to the 11th floor, maybe the height will increase, and as the person goes up, the energy, because you need a lot of energy to climb, so as the elevator. Are we good? I'm running very fast because you can watch out for the first set of problems. All the equations are established over there. You just apply them here and you are good to go. This is quite confusing, but we'll try and break it down. You have to combine the idea of thermodynamics and electricity here to be able to solve the example 4. Now, a classroom that normally contains 40 people is to be air conditioning with window air conditioning units of 5 kilowatts. So we want to buy an air conditioner for a classroom, but it is rated 5 kilowatts. A person at rest may assume to dissipate heat at a rate of 360 kilojoule per hour. So per hour, each person is dissipating 360 kilojoule of heat energy. There are 10 light bulbs in the room, each with a rating of 100 watts. So the bulbs are also going to dissipate some form of heat energy over there. The rate of heat transfer to the classroom through the walls and window is estimated to be 15,000 kilojoule per hour. If the room air is to be maintained at a constant temperature of 21 degrees Celsius, determine the number of window air conditioning units required. So as an engineer, you are brought to make analysis for a room which is to be air conditioning. They will buy 5 kilowatt air conditioning. So make your analysis and tell them the number of air conditioning they will need for that single room. And they are telling us that for each room, there are 40 people and each one is dissipating heat of 360 inside the room. There are 10 light bulbs rating 100 watts. And from calculation, they are seeing that the heat transferred to the room through the walls and the window is estimated to be 15,000. So let's make the analysis. First, we can get our number of people to be 40. We can also get our air conditioning units. Air conditioning unit is 5 kilowatts. But again, we also have heat by each person. So heat by each person is giving us 360 kilowatts. Check the unit per hour. Are we good? We can also know that the rating of the bulb is giving us 100 watts. So each person dissipating 360 kilowatt. What is the total heat by the 40 people? This is very simple. So total heat by people. That will be 40 by 360 kilowatts per hour. But remember, look at for the heat dissipated by the people, it is in kilowatt per watt or kilojoule per hour. The bulb rating is just in kilowatts. We also have the heat transferred through the walls in kilowatt per hour. So we have to change the units either to watts or back to kilojoule per watt second. We know that watt is equivalent to what? Kilojoule per second or joule per second. So I prefer changing all the joule per hour to what? Joule per second so that it will tell you with the watt. Are we good? So changing from hour to second, you have to divide your whole expression by the hour, which is 3,600 watt seconds. And with this, I'm getting 4 kilojoule per second. So the people, the energy, the total heat energy dissipated by the people is 4 kilojoule per second, which is 4 kilowatts watts. Are we good? So let's consider the electric bulb. So each rating, number of bulbs, the number of bulbs is what? 10. And we have the rating the ratings to be 100 watts. So what is the total rating? That will be total is going to give us 100 by 10, and that's 1000 watts. And here too, don't forget we are working in kilo, so you are not going with the 100. So this is equivalent to 1 kilowatts. 1 kilowatt, the same thing as 1 kilojoule per second. It's very interesting. 1 kilowatt. So the total energy by the bulb is also 1 kilowatt. Are we good? Now we are to tackle the heat transferred through the walls. Heat through walls, which is also 15,000 kilojoule per hour. But since I'm working in watts, I have to also convert that back to the kilojoule per second by dividing the 15,000 by 3,600 seconds. And that is giving me what? 4.16 kilojoule per second for the heat transferred through the walls. So now I've made analysis for energy of the people, energy of the electric bulb, and energy of heat through the walls. I can add them to know the total energy or total heat energy coming inside the room before I consider the air condition. So total heat in the room, the total heat in the room is giving us heat by the people, which is 4, plus the heat by the bulb, which is 1, plus the heat by the walls, which is 4.16, and the total heat is giving us 9.16. We can use the kilojoule per second. So inside the room, if all these are in operation, there's 9.1 kilojoule of heat dissipated in the room, and the air condition is 5 kilowatts. So meaning if we buy one air condition, it cannot take care of the heat content. It will be waste because the air condition has a power of 5 kilowatts and the heat inside the room is also 9. So if we want to know the number of air condition to buy to cater for all this heat content, then we have to divide the heat content by the number of air conditioning units. So we have number of air condition needed. I hope it's very simple. Air condition needed will be the heat content, which is 9.16 kilojoule per second or kilowatts, divided by the 5 kilojoule per second, and I'm getting 1.833 for that. So I have to buy 1.833 air condition, and this is not making any tally here. So you have to run into the whole number, making 2. So to cater for the heat content in this classroom, what we have to do is that we have to buy 2 air conditioning units. And you conclude number of air conditioning needed is 2. We need 2 air conditions to cater for this classroom. I hope it's very interesting. You just have to know the analysis of what heat. That's for thermodynamics. If you don't know how heat is working, then all your calculations will be wrong. The units also, you have to change them always. If it is kilowatt, work in kilowatt. If it is joule per hour, work in joule per hour. In the example 3, we decided to work in kilojoule per hour because electricity is what? Rated in kilowatt per hour. That's why we worked in the hour region. But apart from electricity question, you can choose to convert all your unit to joule per second. And with that, you are good to go. Let's start with the chapter 3 from the next episode. Thank you for watching. You can drop your questions at the comment section and I will answer them. Thank you.